Coulomb's law. If we investigate the forces between 2-point charges, for instance these two positive charges, a distance r apart, we get a force F which is repulsive. The two like charges repel each other. If we now reduce the separation to half r, we find we get 4 times the repulsive force. They obey the inverse square law. The force is inversely proportional to the separation squared. Now to simplify things a bit by just considering the force on one charge due to its position close to the other. So again we have our two charges a distance r apart, and just considering the forces on the right hand charge, it would have a force F to the right. If we replace the right hand charge with one of twice the value at 2q, the force will now be twice the value at 2F. Equally, if we'd replaced the left hand charge with one of twice the value, with the right hand charge again having charge q, the force on the right hand charge would again be 2F. So we see that the force is directly proportional to both charges. We can bring these relationships together with this expression, showing that the force is directly proportional to the product of the two charges and inversely proportional to their separation squared. The two charges are sometimes denoted by an upper and lower case q, giving this expression. We can change this to an equation adding a constant of proportionality, where k takes the value of 9.0 times 10 to the 9 newtons meters squared per coulomb squared if there is air or a vacuum between the charges. Just to illustrate this point, here again we've got our two charges a distance r apart, and I'm showing the force F on the right hand charge. If we were to place another material between the two charges, we'd now have a smaller force between them. The property of materials to affect an electric field is called the permittivity and is given this symbol. Problems will generally be set with air or a vacuum, which has a permittivity of epsilon naught, written like this, and epsilon naught has the value of 8.85 times 10 to the minus 12 farads per meter. You don't need to be aware of what farads are at this stage. Gravitational fields have no property similar to permittivity, and the force between two objects is not affected at all by the material between them. Just to complicate matters further, k tends to be written as 1 over 4 pi epsilon naught, and if we substitute into the expression here, we get this. This is known as Coulomb's law. The 4 pi simplifies many equations and is based on the spherical nature of the force. Let's look at an example. Calculate the force between two protons 1 nanometer apart in air. Well, for this we need the Coulomb's law expression, and if we now put in the values with 1 over 4 pi epsilon naught having the value 9.0 times 10 to the 9 newtons meters squared coulomb to the minus 2, multiplied by the charge on a proton of 1.6 times 10 to the minus 19 coulombs, and again by the charge on the other proton. I could have written this with 1.6 times 10 to the minus 19 coulombs squared, divided by this separation of 1 nanometer squared. This gives a force of 2.3 times 10 to the minus 10 newtons. As the charge on both protons is positive, the force here comes out positive, which means it is a repulsive force. If we'd calculated the force between a proton and an electron at this separation, it would be the same magnitude of force, but the minus sign from the electron would give a minus sign on the force, and this shows us that the force is attractive, as you would expect.